Good morning, everyone. Welcome to today's class. It suddenly gets cold, so please stay warm and stay healthy. All right, so let's start with today's lecture. So today we will go into a deeper content about the artificial neural network, that is multi-layer perception. But before that, let's have a quick review about the artificial neuron. Basically, this is what we learned in last week. So recall that the artificial neuron is just a simple unit, a simple biological neural model in the artificial neural network. Through last week, we already see that it has a couple of limitations. First, the artificial neuron can only represent a limited set of functions. So basically, that's the linearly separable functions. It can only distinguish by the value of its output the sets of inputs that are linearly separable in the inputs. And one of the simplest examples of non-separable sets is logic function exclusive OR, XOR. We have seen that if we want to use perception to do this logic function, it doesn't work because this is not linearly separable. And some of you may ask that because for the artificial neuron, actually we can change different activation functions, right? Previously, we only tried perception. Perception can only use the binary step activation function, so perception cannot distinguish the nonlinear separable data. But what about we use artificial neuron with a different activation function, right? Some activation function, actually, they are not linear. Can it work? Actually, still not. Because for a single artificial neuron, if we check it, so for example, this is the artificial neuron. We know basically it just has a weighted sum and an activation function. Itself is associated with a parameter theta, and possibly it's connected with some input. Then it directly gets some output. So this is the artificial neuron. And when f, this activation function, is a binary step, it's called perception. Then what if we change this activation function to a nonlinear activation function? So here is an example. Suppose now we select f to be sigmoid. So f is just sigmoid. If we check f is sigmoid, it's nonlinear, right? However, even we use this nonlinear activation function, artificial neuron can still only distinguish the linearly separable data. Because let's check the sigmoid. Sigmoid is that fz takes 1 divided by 1 plus exponential of negative z, right? This is the sigmoid. And we know the sigmoid basically is just this thing. Something like this. So this is 0, this is 1. All right, this is, suppose it's z, and this is the fz. Then if we want to use this activation function to do some, for example, to do some classification, know that it can only output some continuous number in this range 0 to 1. If we want to use it to do the activation, for example, basically we know this represents the probability, right? Probability between 0 to 1. And in practical use, usually that we set a threshold, and usually it's just this point, 0.5. So that is if the final output fz is larger than 0.5, then we predict it as one class. If this fz is smaller than this 0.5, we predict it as another class. Basically, still we can only use it to do some binary classification 0 and 1 because it represents probability. And then let's check what is this fz. So fz is f of the weighted sum. So here fz, if we look at this one, fc is just f weighted sum xi times wi plus theta. So that means the intrinsic decision boundary is still, we try to check this linear sum, whether it's larger than 0.5 or not, right? If we want to use it to do the classification, binary classification. That means the decision boundary is this one, because when this weighted sum is 0, actually Fz is 0.5. We only want to check whether this Fz is larger than 0.5 or not to do the binary classification, since it represents the probability. And if we look at this decision boundary, it's still just a linear decision boundary. So that's why for all the artificial neurons, even if we use some activation function that is not linear, the decision boundary is still linear. So this is the limitation of all the artificial neurons. Not only the perceptron, but all the artificial neurons, they cannot do some nonlinear separable data set. So this is the limitation. Then how to remedy these limitations? Let's try to consider this one, the output of one perceptron or the output of one neuron, that is the output here. Now, we do not treat it as some final output. Instead, we let it be connected to the input of other perceptrons or other neurons. That is now, instead of this directly work it as output, we connect it with another neuron. And you can imagine just we connect all of the artificial neurons together and to build a neural network. So this makes it possible to extend the computational possibility of a single perceptron, and then we can get some multi-layer perceptron neural network. And this is the motivation to do the multi-layer perceptron to build an artificial neural network. So any questions so far regarding the limitations of artificial neuron? Great. If no, then currently we are already very well motivated to develop such multi-layer perception. Then let's try to see how to do that. So the multi-layer perception, usually we just, for simplicity, call it MLP. This is a type of feed-forward neural network. What is feed-forward? Feed-forward means that the nodes in this network do not form a cycle. So basically, just from the input all the way go to the output. Can never go back to form a cycle. Then for MLP, it consists of 3 types of layers. The first is called input layer. So input layer, as you can see, is just this layer. So we know that basically for artificial neuron, we also have these input nodes, right? So from MLP, we just have a layer to store all these input nodes from x1 to xn, representing now we have some n-dimensional inputs. Usually we just use the index I to represent the input layer, so we call it layer I. And now we have the second type of layer, hidden layer. Hidden layer is just basically all the layers between input and output layer, we call them hidden layers. So in a MLP, we can have many hidden layers, but here we just draw one hidden layer as an illustration. So hidden layer, again, is a layer consists of many neurons, as you can see. Each neuron is just one node. The node consists of the weighted sum, activation function, and the bias term theta. So each node like just be an artificial neuron. We call it layer J. Just use the index J to represent its hidden. Then possibly after some hidden layers, like you can imagine, actually in practical implementation, there are many hidden layers connected here. But at the end, we will have output layer. Output layer is used to give the final output. Output layer, we call it layer K, just use the index K. And again, just some artificial neurons, but all the outputs from the output layer will be working as the direct outputs, the final outputs of this artificial neural network. So this is a typical architecture of the MLP. These are all the inputs, and as you can see, the sum is just the summation, the weighted sum. And note that there are many edges in a neural network, right? Again, each of the edge is associated with one weight parameter. That means basically the number of weight parameters in a neural network is the same with the number of edges here. So as you can see, when this neural network expands, the number of parameters will also increase largely. So, and the neuron has activation function F here. Typically, for the same layer, we will use the same activation function. So that means for this hidden layer, all the activation function F should be the same. And for the output layer, all the activation function F should be the same. But hidden layer and output layer, they typically will use some different activation function. Just the same for the single layer. And theta is bias. Theta is another parameter we should learn in this neural network. So this is the typical MLP neural network. And we already see that it's a feed forward from the inputs to outputs. We can only go this one direction. We can never have something like we return back. Like if you consider if there is like multiple hidden layers and somehow one hidden layer's node has an edge back to the input or back to some previous hidden layer, then we form a cycle. But in MLP, we do not have such cycles. There is another type of neural network who have this cycle. It's called recurrent neural network, the RNN. But in our course, we won't cover that RNN. Then, of course, when you see such an architecture, possibly you will have many questions. Let's try to solve them one by one. First, how to initialize the weights and biases. Now, if we want to train a neural network, then we need to learn all the parameters. According to previously what we learned for artificial neuron, usually we need to initialize them, right? Then how to initialize the weights and the biases in the MLP? The answer is still we just initialize them to some small random values, randomly generate all of these values. Then how to perform the training? So after you initialize the parameters to some small random values, how to perform training? This is illustration of the answer. Later on, we will see some details. So first, we need to let the network calculate the output with the given inputs. And for this step, we call it forward propagation. That is here, starting from the inputs. If you already have all the parameter values, right? If you already know, okay, all these weights, these biases, what are their values, then for any inputs, you can just follow the way to compute the final outputs. This is the feed forward because basically you're just starting from input layer all the way until you get the output. This is the this is forward propagation. After forward propagation, you can get the computed output. Then it's training. So training means that you're dealing with a training data. So of course you already know what is the target label. Then the second step, calculate the error or the loss function. That is the difference between the calculated outputs and the target outputs. Try to compare the true labels and the MLP's outputs. Then, of course, possibly you will get some errors because the MLP during training is not always correct. It makes some mistakes. After you get this error, you need to use this error or this loss function to go back to update all the parameters so that the parameters will be more accurate so that your computed outputs can be closer to the target. And now we will go to the backward propagation. Backward propagation is that we use this arrow. First, we need to update the weights and biases between the hidden and output layer. After that, we update the weights and biases between the input and hidden layer. So that means at this stage, you already compute the outputs, right? And you computed the arrow. You make use of this arrow first to update all the parameters here. The parameters between hidden and output layer, including the biases for output layer and the weight parameters between hidden and output layer at these edges. After you update these parameters and you go to here, so try to update the input layers and hidden layers between these two layers, the parameters, including the hidden layers bias here and also the edges. Each edge is associated with some weight parameter. Of course, if you have like multiple hidden layers, still you follow this direction from output layer all the way go back until you have the input layer. That's why it's called a backward propagation. So basically, it reverses the direction of the MLP, go backward until you update all the parameters. So this is one epoch, if we use the terminology, right? So you have one input and then use that input data to do forward propagation, compute the arrow, and then do backward propagation to update the parameters. After that, go back to step one. So it's not one epoch, it's just one step during epoch. After you do these steps for the whole training data set, that is called one epoch. This is the perform training. Then we also care about when to stop the training, right? We cannot like infinitely go to that. So the answer would be, we can again consider the three possible stopping conditions. First, after a fixed number of iterations through the loop, so we set the maximum epochs. The second is that once the training arrow falls below some threshold, so we care about the training arrow. So as long as the training arrow is small enough, then we stop. Here is a third possible stopping condition is that we stop at a minimum arrow on the validation set. And then you may ask, what is the difference between the second one and the third one? Notice that the second condition is considering the training arrow, but the third condition considering the arrow on the validation set. If we use the third one, then that means our previous training data, we split a small part of it into the validation set. It's just like what we do in the default cross-validation, right? In a big training data, we split just one small part to be validation set. And then we will train on the remaining training data while we test on the validation set. Validation set actually is from the big training data. So we have their true labels. So we can always try to compute the error on the validation set. And once we find that it already achieved some minimum error on the validation set, then we stop. Compared with the second stopping condition, the third actually is better because the third can try to avoid the overfitting problem. If we only consider the training error, then of course we can train very well on the training data, but possibly we will meet the overfitting problem. So if we consider the error on the validation set, that means actually we are also measuring the ability of the MLP to generalize to some new data. So the third one is usually preferable. And note that if we build an MLP neural network, the training can be very slow in networks, especially if we have multiple hidden layers. So you should also get prepared later on when you do your lab 6. Usually the training will be slower than what you have done in previous labs. Like in previous lab 2 and lab 4, basically the model are quite easy, right? But if you deal with this MLP, usually the training might be slower. Like one epoch, it may take like 1 or 2 minutes, and possibly you will have multiple epochs. Yeah, so get prepared for that. All right, so to answer these questions, now we already have a rough idea how this MLP works, like how to update the parameters, how to train it. So until now, any questions so far regarding some basic mechanism of the MLP? Great. This is just a rough idea. Next, we will go into some details how to update. Like in this process, we only have a rough idea. We only know that, okay, we should do forward, we should do backward. But specifically how to do backward, then we need to follow some mathematical formulas to do the backward, to do the updating. Before that, we have to make some assumption. We assume that now the activation function is sigmoid function. So takes this formula, and we assume that the loss function or the error function is the square loss. So that is, it should be the half of the sum of all this big OK minus big TK square, the square of the difference between computed output and target output. We know that K is the output layer, right? We use K to denote output layer. So we take the sum means that for all the nodes in the output layer, yes, actually the output layer can have multiple nodes. So for all the nodes in the output layer, we compute its output and get the difference between the computed output and the true label, the target, and square it and add them up. This is the square loss. So we assume that we have this activation function and this loss function. Note that if we want to develop the formula for updating parameters, then we have to make the assumptions. We have to, because all these formulas are only fixed for some fixed activation function and fixed error function. That means if you change the activation function to some other activation function, or if you change the loss function to another loss function, all of these things will just totally change, because all of them depends on the gradient descent. If you change activation function or if you change the error function, then the gradient or the derivative will change. Then all these things will change. So that means whenever you want to get a formula for updating parameters, you must first assume what is activation function and what is loss function. After you fix these two functions, you can do gradient descent. For this course, we don't require you to know how to do the gradient descent. Like we don't require you to know how to differentiate, like how to compute the derivatives of all the functions. So we directly provide the results for you. So if we already have activation function and error function like this, then the formula for updating all the parameters should be derived by minimizing the loss function using gradient descent. And then we get the formulas like this. So here, big OI is here. This big OI is the input in layer I. We always use this I denote input layer. And we also have big OJ, like big OJ is here. Big OJ is the output of node in layer J, or the output you computed in the hidden layers. And then big OK is the output of node in output layer in layer K. And we also have big TK here. Big TK is the target output of node in layer K. That is the true labels. Then Wij, we use two indexes, I and J, meaning that Wij is the weight connecting node in layer I to node in layer J, or that's the weight parameters between input and hidden layer. Then corresponding, we have Wjk. Wjk, we use J and K, these two indices, meaning that this is the weight connecting hidden layer and output layer, right? So the nodes in layer J to node in layer K. And we also have the bias parameters. Theta J here is the bias of the node in layer J, hidden layers bias terms, and then theta K is the output layers bias terms, the bias of node in layer K. All right, so after we know all these denotions, like we know all these like symbols, what they denote, let's check the formula. The first step, we compute delta K. What is delta K? Delta K means the change of parameters between hidden and output layer. And we know the parameters between hidden and output layer, including Wjk and theta K, right? The bias in output layer and also all the weights between hidden and output layer. So we first get this delta K. Delta K is computed by OK minus TK, the difference between computed output and target, then times OK times 1 minus OK. Later on, we will just have some brief explanation why it looks like this. But until now, we just first try to accept that this is the delta K. After we have delta K, we can use delta K to update the parameters between hidden and output layer. Between hidden and output layer, we have Wjk. So we can first update Wjk to be the old Wjk minus eta learning rate. We still need the learning rate, eta times delta K, which we just computed, times Oj. OJ is previous in forward propagation what you already get in the hidden layers outputs. So this is how we update all this WJK. Then we need to update theta k, right? The parameters in output layer also include the bias terms. So theta k will be the old theta k minus learning rate eta times delta k. After that, we finish updating the parameters between hidden and output layer by using this delta k. We are not finished yet because we still have other parameters, the parameters between input and hidden layer. Next, we need to compute delta j. Delta j is computed by OJ, the hidden layers output, the hidden outputs times 1 minus OJ, then times the sum of delta k times WJK. And if you look at delta j, you will find that in order to compute delta j, you first need to know what is delta k, because delta j is computed according to delta k's value. So that's why we must follow this order. This order is that we first compute delta k. After that, we can compute delta j, because delta j depends on delta k. And that also explains why we have to do the backward propagation. Backward propagation is that we first need to get the change of the parameters here, delta k. Only after we have delta k, we can compute the change of parameters here, that's delta j. So that's why we have to do this direction, this backward direction to update all the parameters. So first compute delta k, then compute delta j. After we have delta j, we can update all the parameters between input and hidden layers. So that is weight parameter wij should be old wij minus eta times delta j times oi. Recall that oi actually is just xi, the input. And theta j, the bias parameters in the hidden layer, should be old theta j minus eta times delta j. After that, we update the parameters. And basically, these are the formulas in backward propagation in one step. And of course, after we fix activation function and arrow function. But now you only know what are the formulas. Still, you don't know why we should do that, right? We already mentioned that all of them based on gradient descent. Even though we don't require you to know how to compute the derivatives of the functions, but still we require you to understand some basic logic of the gradient descent or some basic mechanism. So let's try to see some intuitive idea of the gradient descent. Consider now we have this arrow function like this. Note that the horizontal axis represents some parameter w, and then the vertical axis represents the arrow. So basically this shows the relationship between the arrow and a parameter w. So here we just, for simplicity, assume we only have this one parameter w, and what is like e, the arrow changes according to w, and the changes look like this. All right. If we observe this arrow function, we find that the arrow function has many local minimum. What is local minimum? Local minimum is some point like here, the 0.4, 0.5, 0.7. They are called local minima. Local minima means that it's minimum when we consider a small neighborhood, right? It's smaller than of, it's like small neighborhood, that is local minimum. And in local minima, there are some important properties in that the local minima gradient must be 0 or the slope is horizontal. Then we call it local minimum. But of course, it only has one global minimum. Global minimum is here, the 0.5. Global minimum means that if we look at all the functions, the entire function, this takes the minimum value. That is called global minimum. We only have one global minimum, but many local minimum. Then the intuitive idea of gradient descent is that we start from some initialization and then try to update it try to minimize this error function. So suppose we choose data point 1, this point 1 as some initial weight. That's here. The point 1 is here. And so just suppose our initial value of W is there. And then, of course, we will update it with some certain learning rates. Note that at this moment, the slope is negative. The slope is negative later on because now we want to minimize the error E, right? So we should go to the negative of the slope at that point. So we should go this way because we want to minimize the E. And possibly the next step, we will go to the point 2. And then next step, we will go to point 3 because we always follow the direction of minimizing the error E. And then possibly the next step, we will go to the point 4. And then we stop because we reach some local minimum. After reaching the local minimum, the gradient becomes 0. After the gradient becomes 0, it stops updating. But if we start at some different initial weights, we possibly will go into a completely different local minimum. Suppose we start from the point 10 here. Then the next step is possibly we will go to the point 9 and then go to point 8 and then go to point 7. So we will end up with a very different local minimum. And so actually by the gradient descent, it's not guaranteed to converge to some global minimum. Like for this one, actually it's very hard to converge to this data point 5, right? Only if the initial value is between this range, then we will converge to this global minimum 0.5. For many other cases, we will just go to the local minimum 4 or local minimum 7. So this will be some intuitive idea of the gradient descent. Then let's try to look at some more formalized explanation of the gradient descent. So we try to minimize this function, error function, the square loss. And we can follow the negative of the gradient. What is negative of the gradient? In 2D space, negative of the gradient is just slope. And then we go to the direction of the steepest descent. This is called the gradient descent. So formally, if we have a parameter alpha, so here alpha can be a weight or a bias. Anyway, it's just a parameter in the neural network. Then we start with some random initialization. Suppose that's alpha 0. So we start at this point, alpha 0. And then we move a positive distance. This positive distance is decided by learning rate eta. We move this positive distance eta in the direction of the negative gradient. Then our new and improved alpha 1 will look like this. The alpha 1, here this subscribe 1 means the step. So that means the first step, alpha 1 becomes the initialization alpha 0 minus eta, the learning rate, that's the distance we want to move, times the derivative of the arrow function e with regarding to alpha 0. This is called the gradient descent. We need to get the derivative of the arrow function e with regard to this parameter, use it to multiply learning rate, and we move to the negative direction of the gradient. So it's minus this eta times the derivative, and then we get the new value for this parameter alpha 1. So more generally, if we already at some step, at the step t, the parameter alpha has a value alpha t, then we can turn it into alpha t plus 1. That means the next step after updating, so here the subscribe t represents the iteration step. The alpha t plus 1 is the last step, alpha t minus learning rate eta times the derivative of the arrow function with regard to alpha t. And we update it to alpha t plus 1. So this is the idea of gradient descent. Starting from some initial guess, alpha 0, that's our random initialization, we keep improving the model little by little until we find some local minimum alpha big T. Local minimum means that the derivative delta E with regard to alpha T, big T, is 0. then we have to stop. Why we have to stop? If you look at the updating formula, whenever this derivative becomes 0, then alpha t plus 1 equal with alpha t. Then you cannot improve it anymore. You just stop the updating. So that means whenever you get converge, whenever you get the gradient becomes 0, the algorithm just stops. And it converts to some local minimum. Because for any local minimum, actually the gradient is 0. This is the gradient descent. Basically, it just follows such formula like this until reach some local minimum. And know that this process may take thousands of iterations. So we typically implement the gradient descent with a computer instead of manually calculate all of these processes. This is for some intuitive idea of gradient descent. Any question? Yes, please.
So I've noticed that if there's a very large learning rate, it might stuck in, like, how to say, it cannot really reach even the local minimum. It will jump between.
Yeah. Yes.
Is there like any way to have it to like adjust the learning rate like during the learning?
Yes. Very good question. Yes. Maybe I will explain this to other students first. Yes, the learning rate, we know the learning rate actually adjusts the distance that you move each step. Of course, if the learning rate is very, very slow, then possibly you will take many iterations. Your training will be slow. But if the learning rate is very large, then you will go into some oscillation. Here is an example. That is at this point 8. The next step, possibly you won't go into the step at the point 7. Instead, you go to the point 6. Because the learning rate is too large, then you will jump over the local minimum, go to the left side, go to the point 6, and possibly the next step you will again go to some points here, and then you do this oscillation. So that still actually is very slow because you can't reach the local minimum. Yes, very good point. So learning rate too large, then you do oscillation. Too small, then your training is slow. The eta, usually we call it some hyperparameter. So that means we can try to tune it. Basically, is that you can select different values of the learning rate and then try to run multiple MLPs with the different learning rates and then select the one with the best performance in a fixed number of epochs. So that's how to tune the hyperparameter learning rate. But usually learning rate is a small. Of course, it should be some positive number between 0 and 1. Usually it's very small, like 0.1, something like that. But in different data sets, it may have like different optimal values. But yes, very good question. Great. Any other question regarding the gradient descent or the general updating rules for the MLP?
Would the jump between numbers be the same? Because you said, for example, you have a gradient like this and jump from this point back to this point and then alternatively going back. So are they actually the same point or maybe even actually converging when the learning rate is a little bit higher than?
Not necessarily be the same points. Possibly just oscillate between a small region, a small neighborhood.
So it's like still converging though?
Yes, still converging, but very slow because it oscillates for many iterations.
So, so if it's assuming it to approach infinity, it would eventually go to the bottom line. So still.
Yes, theoretically speaking, it will converge, but practically, yeah, right. Practically, it may take lots of time, so that's we won't wait for it to converge. But theoretically speaking, yes, it will converge.
Then would the delta E be something like a decimal thing?
Delta E will like if it's oscillating, delta E will get somehow smaller and smaller, but still it's may get oscillate a little bit. But in some overall trend, it's being like smaller and smaller until it reaches 0. Yes, thank you. Very good. Yeah. Any other question regarding the gradient descent? Okay, very good. So this is the idea of gradient descent, and basically all of the formulas here are derived according to the gradient descent. That means we are trying to get the derivative of the arrow function with regard to each of the parameter, and then based on that, we compute delta k and delta j and update the parameters in this way like this, all because of the gradient descent. So basically, you can know what is the derivative of the arrow function with regard to each of the parameter by looking at this formula. So for each parameter alpha, it should be old alpha minus eta times this derivative. So if you look at the weight parameter, for example, here, and that means the derivative of arrow with regard to wij is delta k times oj. And the derivative of E with regard to theta k is delta k, and so on and so forth. So basically, this term multiplied by eta is the derivative. And until now, actually, you may have another question, is that actually our motivation is to get a minimum, right? Get some minimum, like here, we want to get some local minima or global minima, and then we choose to compute the local minima by gradient descent. Do we have any other ways to get the minimum? Like, can we do some closed form solution? By the way, the closed form solution is, you can consider it just is an optimization problem, have some closed form answer. Maybe we can take a very simple example here. So just suppose our arrow function E takes this form. So x is some parameter, and arrow function E is just half times x minus 2 square. Actually, for this optimization problem, if we want to minimize E, it has some closed form mathematical solution, right? That is x equal to 2. If we select x equal to 2, this is a closed form, right? We can directly get the minimum. That is when x equal to 2, we get the minimum of E is 0. Directly get it. Why not directly get the closed form mathematical solution? Why should we use gradient descent? Why not look at the minimum using this closed form 1? The reason is that, of course, for this simple example, we can do that. We can easily get the closed form solution, but for most nonlinear regression problem, there is no closed form solution. So possibly the arrow function just does not have the closed form solution, or even for those with closed form solution, gradient descent is computationally cheaper, much cheaper to find the solutions. It's very fast. Even though it possibly takes many iterations, it's still faster than computing the closed form solution. Because for these complicated arrow functions, to get the closed form solution using some optimization algorithm, if you want to implement it, for example, using the C++ or using Python, actually it's very, very time consuming. It involves many of the matrix operations, and the matrix operations to get some optimization problem is very time consuming. So actually the gradient descent is even like much cheaper than the closed form solution. That's why for this problem, of course, it's an optimization problem. We want to get some minimum. Still, we try to refer to gradient descent instead of some mathematical closed form solution. So any question regarding this, why we should do gradient descent? Very good. If no question, then let's take 5 minutes break. After that, we will continue.
say that you're lucky that one of the epochs you've got a good initial value that can be point.
Yes.
Then why we do not use some like stochastic reading sense to help you to like reach to the global minimum?
Yes, actually the stochastic gradient descent is some like improved version of the gradient descent. The gradient descent is the most basic one.
Would it be like very
Not really.
it's kind of similar?
Yeah, kind of similar.
被动. Oh, and I noticed that you always use these loss function, right? I know there's several different kind of loss functions. But is this, how to say, like, what is the benefit of using this loss function instead of?
This loss function is very easy to classify. So actually, in practical ways, we don't use this very often. But to give you some idea of how to do gradient descent, we'll use this.
Just an example.
Just an example. Because it's very easy to actually explain. All right, yeah, after this short break, let's try to clarify some of the questions I just received first question, of course, I know some of you know some other improved version of gradient descent, like the stochastic gradient descent. Later on, we will also mention another algorithm called Adam. Yes, actually, they are the improved version of gradient descent. So that means they are developed or they are designed based on gradient descent. And in the meantime, they can try to improve the gradient descent, improve both in performance and efficiency. So that means they can be faster, even faster than the original version of gradient descent. And also in the meantime, they can try to resolve some problems. For example, they can more easy to find the global minimum. So yes, very good. That means in practical, we possibly will use some improved version of gradient descent instead of the original gradient descent, instead of like this one. But still, it's very important to understand the idea of the very original version of gradient descent. Another question is here. When we calculate delta J, it also depends on WJK, right? Then what is this WJK coming from? Like whether it's in this step or last step. So actually it's from last step. So even though after you have this delta K, you can immediately get the new WJK, but usually just by follow some convention, when computing delta J, still we use the last step's WJK. Because for updating, for backward propagation, the right side, we just by default assume all the right side should come from the last step, should come from the last forward propagation. So here WJK is still from last step instead of the new values in this step. Very good. Another very good question is that like delta K, we compute it, delta J, we compute it, but when we look at the structure here, there are many nodes in layer K, there are many nodes in layer J, right? Then should we just use one delta K to update all of them? Very good question. No, for each of the node we compute delta K. For each of the node here we compute delta J. Note that basically delta K and delta J, they are just the change of parameters for a single neuron or for a single node. So that means if you look at this delta K, it should be the computed output big OK for a single neuron node, the difference between it with the target, and then times OK times 1 minus OK is only for single neuron. And then for delta J, also it's just for single neuron in the hidden layer delta J. Then when we get this sum, like the sum of delta K times WJK, should we get all the output neurons in layer K? Actually, it depends on which neurons are connected to this J. It only cares about the weight parameters connecting with itself. If we use, maybe we can use some simple idea to illustrate that. Okay. Suppose this is a hidden layer. It's a layer J. And suppose now we only care about this node. We call it J1. And then in our output layer, possibly we will have multiple nodes, like here. Just suppose that we have 3 nodes in our output layer, layer K. Then suppose J1 is connected to all of them. Then let's call it K1, K2, and K3. Now, of course, for these 3 edges, they are like connected and associated with some weight parameters, right? So this is a weight parameter here, W. I'll just call it W11. And this is W12. This is W13. Then when compute this delta J1, so know that this delta J basically is one value for each single neuron. So delta J1 will be different from like other delta J's in this layer. Delta J1 should be big OJ1 This is during forward propagation what you computed for this node times 1 minus big OJ1, then times the sum. The sum is the sum of all the output neurons that are connected with J1. So the sum should be delta K1, right? Because K1 is connected with J1. Delta K1 times W11. K1 connected with J1 with this weight W11. And then sum delta K2 times W12 plus delta K3 times W13. So this is specific how we update delta J1 in this example. Then after you compute delta J1, you can use this delta J1 to update all the parameters associated with this node J1. So that means all the weight parameters between input and this hidden layer, like the parameters to the left. That's back propagation, this delta J. And imagine that what if J1 is not connected with this K3? That means J1 only connected to K1 and K2, only associated with W11 and W12. If in this case, then when you compute delta J1, no need to add this one. Because K3 has nothing to do with J1 if they are not connected. So when compute this delta J for each hidden neuron, please try to get the nodes, the neurons connected with it to get what is the corresponding sum. So even though we just try to summarize all the parameter updating rules here by some very concise formulas, but when you apply it to some specific learning process, you need to find the formulas with the nodes one by one. And you need to figure out depending on which nodes are connected together. Yes, a very good question. It's very good that you think lots about the gradient descent and also MLP learning so that you can have many good questions. So any more confusion regarding to this one? All right. Later on, actually, we have a practical example so that you can understand how to do that. Then let's have a review on the sigmoid activation function before we go into that practical example. For multilayer perception, the sigmoid function is used as an activation function for neurons since it is continuous and differentiable. That is, it can be used to find the weight updating rules easily. Now, we can see why it's so important to have the activation function to be continuous and differentiable because of the gradient descent. Because we always need to compute the derivatives of the arrow function, then it's very important the activation function should be continuous and differentiable. We know the sigmoid function sigma x like this, and it has the S shape. And then let's try to say what is the derivative of sigmoid function. The derivative of sigma x with x takes this form, z times 1 minus z, where z is sigma x. That means the derivative of sigma x with regard to x is just sigma x times 1 minus sigma x. Does this look very familiar? If you turn back to the updating rules, you will find that it occurs for delta k and delta j. When compute delta k, it has such term ok times 1 minus ok. When compute delta j, it has this term oj times 1 minus oj. Actually, these repetitive terms comes from the derivative of the sigmoid activation function, because the derivative of sigmoid is sigma x times 1 minus sigma x. So that's why these terms just happens all the time when updating the parameters. Just try to explain why we have such terms. Just comes from the derivative of sigmoid. All right, then let's now try to summarize the whole learning steps for MLP. First, we do forward propagation. Forward propagation is quite straightforward. You run the network forward with your input data to get the network output. Then we will do backward propagation. Backward propagation, for each output node, we compute what is this delta K. Then for each hidden node, we compute what is this delta J. And then we can update all the parameters according to delta K and delta J. By using delta K, we can update the parameters between hidden and output layer, that's WJK and theta K. And by using delta J, we can update the parameters between input and hidden layer, that's Wij and theta J. And eta denotes the learning rate. So typically, eta is a value between 0 and 1. It's a positive small value. So this is the whole learning process for an MLP. Then let's try to solve a practical problem using all of these formulas. So previously, we found that artificial neuron cannot classify or cannot represent the exclusive OR, the XOR logic operation. Then let's try to see, after we have MLP, can we do that? So we know the truth table of logic XOR is like this, right? So only if X and X2 are different, the target is 1. And then suppose we will learn an MLP structure like this. So the input, of course, should be 2D. We only have 2 input nodes, X1 and X2. And suppose we have one hidden layer. This one hidden layer has 2 neurons, and we only have one output layer with single neuron here. And suppose we just use the sigmoid activation function for all the nodes. Sigmoid activation function, so that means the output should be some value, continuous value in the range 0 to 1. Then we need to do initialization, right? To start with the learning process, we have to do some random initialization. Just assume that we randomly generate all the weights and biases like this. They are just some random values, and then we select eta to be 0.5. Activation function already selected at the sigmoid. And note that now in total we have 6 weight parameters and 3 bias parameters. So this MLP model in total has 9 parameters to learn. Then let's start the learning process. Round 1, step 1. We do forward propagation. We pass the first data 0, 0 to our MLP. Here, 0, 0, the actual output T is 0, and the weights and bias are randomly generated like this. Forward propagation is that we just follow the direction of the neural network, right? So when this node, the first hidden node, receives 0, 0 as an input, then we can compute what is this sigma 1, the weighted sum we get, okay, just 0, and then the output OJ1, the first hidden node, should be the activation function f, takes the sigma 1 plus theta 1, which is 0.5. And similarly, we get what is the sigma 2, the output here in this hidden node. And we get, okay, its output OJ2 is 0.5. Note that we must record all of this big OJ1 and big OJ2 because later on we need to use them to do back propagation. So we must record all of them. And then we get the final output, OK, big OK there as this value like 0.43, something like this. We record OJ1, OJ2, and OK. After that, we finish the forward propagation. Forward propagation, very straightforward, right? You just have inputs, and according to the current parameter values, compute what should be the final output. Of course, you also need to record all the hidden outputs. And then we do backward propagation. Backward propagation, previously in forward propagation, we already record OJ1, OJ2, and OK like this. Then, according to that formulas, we first compute delta K. Delta K should be OK minus TK times OK times 1 minus OK. For this MLP, we only have one single output neuron, so we only have one delta K to compute. After that, it's just 0.107, something like that. And based on this delta K, we can use it to update the parameters between hidden and output layer. Delta K will be used to update the parameters here. So including W5 and W6, these two width parameters are connected to this K, node K. And also theta 3, because theta 3 is a bias term associated with this output neuron. So based on this delta K, we update new W5, new W6, new theta 3, just by following that updating rule. Then we also need to compute delta J. Note that in our hidden layer, we have two hidden nodes. So actually, we need to compute delta J1 and delta J2 for these two nodes because they're different. Delta J1 should be OJ1 times 1 minus OJ1, then times the sum of delta K times WJK. So even though it's the sum, but we only have one single node in output layer. So this sum will just be this one, this delta K, this is delta, this is the delta K times this WJK. Note that this WJK we use the last step, that is our initialization here. This is negative 0.86. All right, then delta J2 will do the same thing. It should be OJ2 times 1 minus OJ2 times this sum, but actually it's not a sum because now we only have one single output node. So after that, we compute delta J2. Then according to delta J1, we can update all the parameters associated with this node J1, right? Let's try to see what parameters are associated with J1, this node. It includes two weights, W1 here and W3 here, because these two edges are connected to J1. So use this delta J1, we update W1. And sorry, it should be, this one is, okay, sorry, this is W2. Sorry, this is W1, this is W2 connected to this delta J1. So delta J1 is used to update new W1, new W2, and new theta 1 because these three parameters are associated with the node J1. And then after we have delta J2, we need to use this delta J2 to update all the parameters associated with J2. That includes W3 here, W4 here, and of course theta 2 itself. So after delta J2, as you can see, W3 is updated using delta J2, W4 updated using delta J2, and theta 2 is updated using delta J2. Of course, when you're updating all these weight parameter W1, W2, W3, W4, you also need to get the corresponding input. W1 should be connected with the input X1, right? It's connected here. And W2 is connected with the input X2. W2 is here. W2 connects X2 with J1. So you also need to find the corresponding input nodes. And after that, all the parameters are updated. We finish the round 1, step 1's backward propagation. This is one single step in MLP learning. MLP learning, first forward propagation. After forward propagation, you use the arrow to update all the parameters in backward propagation. This is only one single step. We have many steps to do. Like round 1, step 2, basically we do the same thing. We pass the second data point 0, 1 to our neural network, and the target output T is 1, and we already have all the parameters updated in last step. These parameters are come from here. Already updated them, and then we do forward propagation. For this input, we get its output at 0.377, and we also need to record this OJ1 and OJ2. They will be used in backpropagation. Then backpropagation, you repeat all the computations using the formulas. First get delta K, and delta J1, delta J2, use them to update all the corresponding parameters. After that, we finish round 1, step 2. Of course, there are many steps to do that. So at the end, now we come into the round 10,000. I'll just jump over all of the middle steps because actually we won't manually calculate that. And this is the round 10,000 step 4. After that, we do the backward propagation, get all of the parameters like this. Then in round 10,001, we do one more step of forward propagation, and we get that, okay, for x1, x2, 0, 0, y is 0.016973, which is already very close to our target value 0, right? 0, 0 has a target 0, and for the second data point and the third data point, 0, 1 and 1, 0, their output is like 0.98 something, which is already very close to our target 1. And for last data point, very close to its target 0. So basically, we can stop now because this MLP can already be very accurate to predict for all of these 4 training data. But of course, that's the training already after 10,000 runs. Yes, no one will manually calculate that until the round 10,000. So typically, we will just write some codes to implement it and to try to execute the calculations for us. And this would be how to implement this MLP from scratch. From scratch means that we will just manually define all of the parameters and then manually encode how to update, how to do backward and forward propagation. And note that this implementation is only for this model, this structure. So we already fixed that the structure must look like this. All right, then let's see how to do that. We import NumPy. We only import this library because we want to implement from scratch. And then we have our constructor, init. The init, we will initialize all of our parameters and also the learning rate as well as the maximum iterations. So wij, we initialize it to be a 2D array which stores these 4 weight parameters, W1, W2, W3, and W4. And self.wjk store the weights between hidden and output layer is again a 2D array, stores W5 and W6. Then self.tj stores the biases of hidden layer, theta 1 and theta 2. And then self.tk stores the bias in output layer, that's theta 3. And note that later on, to make sure that all the computations, they are compatible, we already initialize all of them to be 2D arrays. So yeah, it's very convenient if at this initialization moment we keep their dimension to be the same. All of them are 2D arrays because later on, if you do not have the same dimension, later on you will possibly have some trouble. All right, all of them are 2D arrays, and then we initialize the self.learning rate 0.5. We also set the max round 10,000, so we will only train as many as 10,000 rounds or 10,000 epochs. All right, so this is our initialization. Then we define a helper function, the sigmoid. Sigmoid takes input z. This z is the weighted sum we pass to the sigmoid. We want to compute sigma z. And we also have an indicator sigcar. Sigcar by default is false. What is this sigcar? This sigcar is a flag to indicate whether we are in forward propagation or backward propagation. So if sigcar is true, then that means we are in the forward propagation. In this case, we directly return the sigmoid function. It's 1 over 1 plus exponential of negative z. If sigcar is false, then that means we are in the backward propagation. In backward propagation, we do not return the sigmoid. We return the derivative of sigmoid. And previously, we've already seen that the derivative of sigmoid is z times 1 minus z. So in this case, we return z times 1 minus z. So again, this sigma indicates like whether we are in forward or backward propagation. Maybe make some denotations here. So if sigma is true, then we are in forward propagation. If this sigma is false, this way, then we do. That means we are in the backward. And in forward and in backward, we return different things. So very convenient, we just implement it in this single function sigmoid and use this indicator. All right, after defining this helper function, we have a forward function. In this function, we just do all the forward propagation computations. So forward, we accept one data, x, and we have another indicator, predict. This predict used to indicate whether we are in training process or prediction process. Predict is false, then that means we're still in the training process. If predict is true, then that means we go into the prediction process. It will differ because in training, we have to return a tuple. Because in training, we need to restore all the middle results, right? Even including the hidden outputs. But if we are already in testing, in prediction, then we only need to return the final outputs. So basically, there is this only one difference at the final output. So let's see what will be done in forward propagation. Forward propagation, first we get the training example as a column vector. So we reshape x into an array with shape 2, 1. Get this sample. Again, because we want to make sure that their dimensions are compatible. For later on, we need to do some mathematics, that's specifically the matrix multiplications. And then we compute the hidden node outputs. Hidden node outputs yj is first get the weighted sum. Weighted sum is wij times x plus theta j and get the sigmoid. Since it's forward propagation, right? So we let sigma be true. So that means we are in forward and we will return the sigmoid of this weighted sum, store them in the yj. And then we compute the output of the node in the output layer. So yk should be get the weighted sum wjk times yj plus theta k. And again, the sigma should be true. We need to get the sigmoid function and store it in the yk. And if predict is true, we know that we are in the testing step or prediction step. X is a testing data point. In this case, we directly return the final output of MLP, that is yk. If predict is false, then that means we are in the training process. In the training process, x is a training data point. We have to return this tuple. We return the data sample x itself, yj, that's the hidden node outputs, and yk, the output layers output, because all of this will be used later to do the backward propagation. So this is the forward propagation, but until now, I think possibly some of you still have the confusion why yj and yk will be implemented in this way. Why we do a dot product here? Why we first transpose wjk and then do a dot product here, right? Even though, of course, I know you already get very clear of all of the updating mathematical formulas, but how to convert those mathematical formulas into this array dots may not be very clear. So next class we will continue to try to expand all the terms here and to let you know indeed we can efficiently implement all of this yj and yk using this dot product. So we will continue with this in next class and see you on this Thursday. For the midterm coverage, basically it will just be what we end here today. the coverage from the lecture 1 to what we end here today. And later on, I will also make an announcement within today so that you can have more information about the midterm exam. Yeah, so please have a good review and see you on Thursday.